So today we will discuss about group method of data handling. And about this group method of data handling, you have to know just 4 points before working with it. Just be informed about these 4 points. That will be enough to know about the capacity of this technique in case of data analysis, data mining, and data processing. Okay, so group method of data handling is actually a higher version of simple neural networks that uses simple function to model Y or the output based on inputs and some weights. Now you see the simple neural network requires 4 parameters to be estimated. First one is the network topology. What is it? The network topology is, this input, number of input and output is fixed. You cannot change it. Suppose there is a problem where you have 4 inputs and you have to predict 1 output. You cannot change 4 and 1. So what we can do is, or a very important point to note is that even if we have 4 inputs, not all the inputs are equally important for predicting the output. Some were highly correlated with the output, some were partially correlated with the output, or some were very weak correlation with the output. So if we use only the most correlated input for modeling the output, then the convergence rate or accuracy of the model developed with the help of that neural network increases. So the number of inputs is one of the most important parameters in case of neural network modeling. Another important parameter is number of hidden layers. So if I take the example of the simple neural network, suppose there are 4 inputs, x1, x2, x3, x4, and now you have only one output y1. So all are interconnected, right? And each of these connections have a weight. And to predict this y as a function of these weights and the number of inputs. So what happened is, according to the graph theory, what we do is, these are all incoming connection towards this output node. So these are all input nodes, x1, x2, x3, x4, representing the inputs, and this is y1 is the output node. And all this graph or this interconnection between this x1, y1, x2, y2, x3, y3, x4, y4, these are all incoming. So as the or as per the rules of the graph theory, y1 can be taken as equals to xn into wn summation, where n stands for 1 to 4 in our present example. So now you will say that so how this correlation between x1, x2, x3, x4 with y1 is encoded in this model, in this y is equal to summation of xn into wn, n is equal to 1 to 4. This is simple summation. Now you note that here we know what is x1, we know what is x2, we know what is x3, and we know what is x4. But what we do not know is what is w1, w2, w3, w4. So these are all variables. And as is the case in optimization problem, we try to find the best output y with the help of the inputs or design variables, correct? So here the design variable is the wn, because we do not know what is the weights are there, and these xn's are constant here because we know what is x1, x2, x3, x4. So we try to change the value of this wn, all of them, w1, w2, w3, w4 at each iteration, and we multiply them with their respective inputs, and we add them and to get the y predicted. Then we use a fitness function like relative error, where we use this formula, that means y predicted, y actual divided by y actual, and you can multiply 100 to get percentage relative error, or keep it as it is to get the relative error. And if your relative error is within the desired level, we take that value of w's for which you get the that desired accuracy or error. As you know that that is the basic of the neural network, simple neural network. Now these w1, w2, w3, w4 you see are mainly responsible to equalize LHS RHS with LHS. Is it correct? To make y1 equals to summation of xn into wn, we cannot change xn's, we can only change w's. So these w's are responsible for equalizing y1, equalizing with the y1. Correct? So it's very imminent that if I can introduce more w's into this equation, then the convergence rate or the accuracy level that we desire can be enhanced or can be achieved with a higher rate of, or with a lesser number of iterations. So what we do is we try to introduce another layer of nodes in between this input and output. So what happens is you come from here to here. So this entire simple network now can be transformed into this type of networks. So this is our hidden layer, this is our input layer, this is our output layer. Because the advantage of introducing this hidden layer is we are getting more weights, so we are getting more variation to change the RHs such that we can achieve Y at a greater accuracy level and for lesser number of iterations. But let us see how it happens now. Now what happens is, as there is another layer, hidden layer here. So what we'll do, when we'll consider this input and this H as output in case of the first two layers, and in case of the second layer we consider this hidden layer as input and this last layer as output. So what happens is that, so this become like this. So each input will act as the input to this hidden layer first, and this will be common for all the input nodes. So each of the inputs will be connected to each of the hidden nodes. As you know, if I consider these things, these are the nodes. These are the input nodes, but this layer is known as input layer. So a group of node is actually the layer at the same level. So this group of node at the same level is the hidden layer, and this single node at the same level is the output layer. So at the second phase, you see, first phase is input to hidden, second phase is hidden to output. Here also all the input will be connected to the output. If it is not so, then that input is not a input of that output, correct? If an input is not connected to its output, then it is not the input of that output node. So now you see how many weights we can introduce. For this case, there are only 4 weights. Now for this case, you see 1, 2, 3, 4. So from each input and hidden, we have 4 connections. So for I1, there will be 4 connections. For I2, there will be 4 connections. For I3, there will be 4 connections. And for I4, there will be 4 connections. So in total, here we get 16 weights. Each connection is a weight. And in case of this hidden to output layer, there will be 1, 2, 3, 4, another 4 weights. So in total, we will have 20 weights. So instead of 4, we are now having 20 weights. So naturally, this is one kind of discretization. And so at the first discretization, what we are doing is we are discretizing this. Suppose this is the straight line. We are discretizing this into 4 parts. But in the second case, this case, more complex case, we are discretizing this straight line into 20 parts. Are you getting my point? So as the discretization, the discretization is more intimate in this case, more detailed. So the level of accuracy will be better for this, not for this. Right? Say, take for the example this watershed case. When I take a lumped watershed, that means the entire watershed is 1 gauge, and this is the only outlet, and we try to model the outflow from here. The accuracy we get If we compare that accuracy with the accuracy of when we discretize this watershed into its gauge, different multiple gauge stations representing one of the each of the substations or sub-basins, then the accuracy level is certainly higher. So the difference that exists between this lumped and distributed hydrologic modeling, the same difference exists between the simple neural network modeling and complex neural network modeling. So this is more discretized, more distributed, whatever you say, but this is lumped. Clear? Now come to the next part. Here, this y is equal to summation of xn and wn. It is a simple equalization equation. So we change w's to achieve the value of y1, correct, in our iterations. But what happened is that to make those iterations faster, we try to excite this RHS by using something known as activation function. Activation function. This function can be anything, e to the power x, where x will be this RHS. It can be sin x, where x is this one, this entire summation of all the inputs into its weightage. Okay, so you can use any type of trigonometric function or statistical function or sigmoidal function, any type. So this is known as activation function. And this activation function exists in between input and hidden, because basically in case of input and hidden, this is your input and this is your output. This is your input and this is your output. So basically this thing is actually this thing. If I say this is A and this is B, so basically this A is equals to B. So, and again, for this case, hidden to output, now hidden is input, output is output. So if I say it is C, so basically A is equal to B is equal to C. So in case of A, there will be one activation function. In case of C, there will be another activation function. Okay, so what happened is that, let me say that in case of this complex network, neural network, for each of the hidden node, we will have something like this activation function and xn into wn summation. ठीक है? मतलब function of summation of xn multiplied by w. For each one there will be one function, for each two there will be one function, for each three there will be another function, for each four there will be another function. And the same thing what happens in this case of so what happens is actually so the for this first layer so there are these are the inputs and these are now the outputs. So we have four outputs now. So for each one there will be one function of summation xn wn, right? For h2 there will be another function, summation of xn wn. For h3 there will be another one, for h4 there will be another one, as usual. Now from h1 to this, the output, the real output, so we'll have this connections. So here also what will happen, for y1 there is single output now, so there will be another function g, activation function, of summation of hn, or rather let it be hn wm. This is clear. So because this will be h1 w1 plus h2 w2 plus h3 w3 plus h4 w4 equals to y1, not exactly equal. So we are using some function to enhance this equalization. But now you see this hm is actually h1 w1 plus h2 w2 plus h3 w3 h4 w4, right? So this is actually the function of h1 w1 plus h2 w2 because the connection weight between h1 and y1 is w1, this is w2, this is w3, this is w4. But we already know what is h1 is, this one. What is h2 is, this one. What is h3 is, this one. So this is h4. So you put this equation now, that is, this one, this RHS. Say this A, this B, this C, this D into here in place of H1, H2, AC, H1. So the moment you place it like this, the W's of this H1, this H2, this H3, this H4 will be incorporated into this single equation. So basically what happened, y1 will become then equals to g of these functions of summation of x's, x, m and wm's, and these wm will actually will be from w1 to w20, correct? But these xm's will be actually this will be m and let it be n. So these will be actually m1 to m4. This let it be m also, m1 to 4. Okay, so what will happen now? In case of simple neural network, there is only 4 weights and one activation function which are trying to equalize LHS with RHS. But now there is 20 number of weights and 5 activation function, correct? This 1, 2, 3, 4 and overall 5. So 5 activation function which will now try to equalize LHS and RHS. So as the team has enhanced, the members of team has enhanced now, so certainly accuracy will increase because When we are using that simple neural network, we are using in a lumped form. And when we are using this one, complex neural network, we are using in a discrete form. So now why I am discussing about this in case of GMDH. So whatever I have discussed till now is feed-forward neural network. Now what is this GMDH, group method of data handling? It is also known as the polynomial neural network. Practically speaking, the main difference between these two is when we are using an activation function in case of feed-forward neural network, we generally use some linear functions of I think single order equation. But in case of polynomial neural network, the name itself suggests it is polynomial. And when it is polynomial, it is nonlinear. So instead of sine x, we use sine square x. And not only this, what we do is that in each node, we can use different activation functions or subset of those functions or different components of those functions, which are known as partial functions or partial models. And based on some external criterion, after the end of each iteration, we determine the fitness of the model, the accuracy of the model. And accordingly, we can change those functions. So let us try to summarize the things that I discussed. Here, as you can see, we are trying to determine the value of y with the value of x and w, where x is constant, but w is variable. So w is actually the design variable. And this w is one of the most important parameter of neural network. So this is parameter 1. I have initially said 4 parameters to estimate for neural networks. So this is one of the parameters. Second parameter is type of activation function. I am saying that f, g, these are the activation function. We can change those functions and measure the accuracy for those functions and compare to the previous function that we have used. And then if the current function is more accurate compared to the previous function, then we move on with the current function. Otherwise, we move on with the previous function or we try to introduce another new function. So at every iteration, these changes happen. So this activation function f is parameter 2. Third parameter that I have said, this f between input and hidden layer is parameter 2, and activation function between hidden and input layer is parameter 3. Correct? Because we are using, as this is output and this is input, when we are comparing x1 and h1, we are using an activation function. Then again, when h1 is input, y1 is output, we are using another activation function. Both these two activation functions can be same or different. As per the requirement, we changes like that. There is no restrictions on it. Now, so these 3 parameters is over. And lastly, that was first I am talking about network topology. Here, this is the parameter 4. So here we decide mainly we decide what will be the number of nodes in the hidden layer or number of layers in the hidden layer, right? This is hidden layer. I say group of nodes in the same level is a layer. We can either increase or decrease the hidden layer, or we can increase or decrease the hidden nodes. Whatever we may do, we are increasing the number of weights into our iterations. Advantage is it will be more discretized, more distributed if I introduce more weights. But the limitation or weakness is, or disadvantage is, that it will be very heavy, and if the network is very heavy, the number of processing will be much higher compared to a lighter network. You can easily see now when there is no hidden layer, we have to do only 4 arithmetical operation. Multiply W with X, add WX with the other inputs product, and then use the activation function. That's all, and you use the verification with the fitness function. This is the 4 steps that we have to follow. But the moment we introduce this hidden layer, now you see the steps have increased. Because we are getting some more accurate results, so the working of the computers will also increase. The requirement of computational capacity will increase also. The more you increase nodes, more you increase hidden layer, more capacity of computation will be required. So this is the disadvantage part. But the advantage part is that you get a more distributed or discrete network. So the chance of getting the more accurate result is higher also. So that trade-off you must achieve. Now is the catch. In case of simple neural network, feed-forward neural network, or feedback neural network, or recurrent neural network, we try to estimate this parameter 1, 2, 3, and 4 based on trial and error, or by using some search algorithm like genetic algo, ant colony, particle swarm. So we try to do it in a trial and error basis. So in first iteration, we get some output. We verify its accuracy with the actual output with the help of this relative error, and then if the error is lesser, we try to iterate in that direction. If the error is larger, we try to recreate that process with some new weights or new activation functions or the new topology. We try to recreate it, and again we try to verify the accuracy with the help of the fitness function, that is relative error. So there is no restriction that you have to use relative error. You can use anything. You can use mean square error, you can use bias, you can use correlation coefficient, anything of your choice. But majorly or normally we use the relative error. So in case of GMDH or polynomial neural network, the advantage is that they have a capability to self-update. In a single iteration, what they will do, they try to change the activation function in a single iteration and automatically adjust the accuracy with the help of the desired fitness function. So this is automated, this is self-updated. It is not made by the help of trial and error. It is self-updated. In single iteration, they are generating randomly the activation function, then they are randomly they are creating hidden layers, randomly they are creating activation functions, randomly they are creating hidden layers, and then they are testing the fitness function by comparing the predicted output with the actual output. If the fitness function is higher or they are more accurate, then they are moving towards that. If not, then they are changing the or recreating the entire thing in the second iteration. But in the that iteration is a sub iteration of the parent iteration. That means if we are doing first iteration A, within that A, this entire self-updation is going on. Okay, and the most accuracy that it can achieve in A is updated in the memory. Then the next iteration B starts from that level and try to enhance that level. And that optimization or enhancement that B can achieve is stored in the memory, and then C is started, and so on. Ultimately, based on the number of iterations we allowed or the desired or the level of accuracy we have desired, iteration stops accordingly. So the advantage is lesser number of iterations in this case and higher chance of getting a more optimal result. And also that I am saying, in case of network topology, you can change the number of inputs also. You can retain only those inputs which have significant correlation with the output. Those with less or weak correlation with the output is ignored itself at the first iteration A. This is also done in a self-updation mode. They do not require any trial and error to determine which are the more significant input or less significant input. They have a fitness function. In the single iteration, they are generating randomly the values. Randomly, with those values, they are generating the outputs, and they are comparing with the actual output. And based on that fitness value, they are determining whether they are better than the previous or worse than the previous. So according to the result, they are retaining the most significant inputs. So you see, in this case, the estimation of parameter 2, 3 and 4 is completely automated or self-updated in case of GMDH. And in case of the first parameter, the most important parameter of neural network, the weights. In case of simple neural network, you can use one training algorithm at a time. You can use quick propagation once. After you finish it up, then you can take CGD, conjugate gradient descent training algorithm. Check the accuracy level. If CGD has more accuracy, then you go with it. Otherwise, you go with QT. So you have to manually run this training with different training algorithms. But in case of GMDH, this process is completely automated. In one single iteration, they are using 100 or more training algorithms. And with the help of the fitness function, what they are doing is they are retaining only the best fitted training algorithm in its memory. So actually, all these four parameters are self-updated. Within a single iteration, this GMDH is enabled or have that capability to find the most accurate results with the help of these four parameters. This is the main advantage of GMDH. So now to gist it out, to summarize, group method of data handling, you see the group method of data handling is a family of inductive algorithms used for computer-based mathematical modeling of multi-parametric data sets. Right? So GMDH is based on self-organization principles and perform well in complex nonlinear systems. So here you see, I have already discussed about the partial models. In order to find the best solution, GMDH considers various component subsets of base function called partial models that I have said. You can change the activation functions into different partial models. So this method was actually developed in the year of 1968 by Alexei G. Ivanenko, a professor of Kiev Institute of Cybernetics. And the equation used is this one. This y, this is your y1, and this I think you know what is this. This a0, ai, these things are coefficient. A is the coefficient, x is the inputs, this xi, j, k, these are all the inputs, and this n is the number of inputs available in case of that network. So these inputs can also be sorted, and the most significant inputs will be retained, as I have described earlier. So the 4 points of GMDH is actually, it is a polynomial neural network, so it is nonlinear, and normally the relations are nonlinear in real life, so the accuracy level certainly is more compared to simple neural network, where only linear functions are used. Second is self-update network topology. I have explained this. Network topology, the number of inputs and number of hidden layers and nodes are self-updated based on the values of fitness function for different topology. Only the best fitness function and its corresponding network topology is retained. All other network topology is obliterated. Also, yes, this one is also self-update member of inputs required for most accurate output. I have explained it. And I have also explained it allows to use around 100 training algorithms for estimation of the weights, as I've said. In one single iteration, it implements the training with the help of 100 different algorithms. And it retains that algorithm, that result of the algorithm, which has the best fitness function. Suppose you are using 100 and the 54th training algorithm gives you the best result, then it moves with on 54th training algorithm only. That means that best result is retained in its memory, and the prediction is done with the help of that result. Okay, so these are the 4 things. One is polynomial neural network, second is self-updated network topology, that is no need of trial and error, no need of manual intervention. It will decide how many hidden layer and hidden nodes it will use. Self-update member of inputs, that also it will decide. It only retains the most significantly correlated input for that problem. Rest they ignore. And this method, GMDH, group method of data handling, allows to use around 100 training algorithms at a time for estimation of the weights. Correct. So this is your equation. So this is A is the coefficient. Actually, A here is the weights, that is iterated changed. X, I, J, K is the inputs, and not actually the hidden node. As you can see in case of single layer, this H1, H2, H3 was replaced with the X1, X2, X3, right? Because H1 is equals to the function of weights of the input layer and the inputs itself, correct? So whenever you are importing those two, the X and weights of X in place of the H's at the output, hidden layer to output layer functions. That means Y is the output. It was the function of the summation of the hidden layers into the weights of the hidden layer, right? And now, as you know, what is the hidden layer in terms of this function and weights of X and weights of the X's. X means the input layer. So this hidden H is replaced by X whenever you imported it. So here also, in this case also, only the X's has been shown. The hidden nodes and nodes were not shown here because this is the end result. This equation is the end result. So already the hiddens are replaced by the inputs. So that is why you cannot see the hidden, only the inputs layer. Inputs are xi, xj, xkr can be seen in the equation. So 4 points of group method of data handling that you must know. Polynomial neural network, self-updated network topology, that means it determines how many number of hidden layer and nodes it will use by itself, not by any manual interventions, but based on a fitness function. And it can self-update a number of inputs it will retain based on the fitness function, and as well as that fitness function itself will decide that which inputs are the most significant. So those will only be retained. And then 100 training algorithms you can use at a single time for determination of the weights. So in short, this is what GMDH is. So you see, I am saying fitness function, that fitness function is also the external criterion, it is same. Okay. So if you are using relative error as fitness function, the minimum value is the most fitted values, right? Minimum the error, more is the accuracy. So more reliable is the developed model. Okay, so this is what we have to say regarding the GMDH thing, and that is all I want to discuss today. Thank you for your patience hearing, and if you like this lecture, kindly subscribe and like the video. Thank you.